So there's a canonical map. There's always a canonical map if you have a full inclusion that has both adjoints. There's always a map automatically from the right adjoint to the left adjoint. It goes through the general object. You include the points into the space, and then you collapse the space to its components. And that composite is a map which lives in U, if you like. It lives in E, but it even lives in U. And that you can think of as placing the points into the piece that they belong. So this is a canonical map that places each point in the piece. Now when I talk about points, of course, that's not a set. There are maps from one, which you can say those are the bare points, but in general, it's somehow the objective points consists of more than just bare points. And one of my axioms now, special axioms for cohesion, beyond the request, I should first say P lower street should preserve finite products. The typical situation is it's defined as a left adjoint, so it automatically preserves whatever colimits you have, but in general there'd be no reason for it to preserve the limits. But no, we insist that it should preserve products, finite products, not to preserve equalizers and pullbacks. Otherwise, most of the structure would disappear. Maybe, might in some case also preserve, but certainly in the general theory about combinatorial topology, taking the components certainly doesn't preserve equalizers. Imagine, I can write it here. Right? In other words, here's f and g. X, pi 0 of x is 1, i.e. it's connected. If I take the equalizer, so I have two maps from x to y. I take the equalizer, well, in my picture it's just these 2 points. So if I apply the functor pi 0 to this diagram, it's no longer an equalizer diagram. Because actually both of these are 1, I should say, to make it clear. Both x and y are connected. So the equalizer is not connected. So pi 0 doesn't preserve the equalizer. And by the way, this is typically how you construct non-connected spaces, right? The real line is connected, the complex numbers is connected, but by solving equations, you produce objects of non-trivial combinatorial form. So, but it should preserve products. Should preserve products. So that's one of the axioms, besides the existence of these adjoints. Another one is the nullstellensatz. Now, what do I mean by the nullstellensatz? Nicoletta was complaining the other day about how in school they teach you to take the equation of a line, put everything on one side and 0 on the other side, not knowing why you do that. Of course, the reason why you do that historically is the fact that you work in rings that have subtraction, and so you can translate any equation into an equation saying that some other thing equals 0. This is sometimes very useful. Of course, everybody knows it has the great usefulness that if you can factor that thing, then you can tell a lot about the roots using the factoring. But except for that, it's a bad thing, because this whole business of subtraction, 0, and so forth, has really, in general, nothing to do with the issue that two things could be equal. So anyway. Anyway, I'm just explaining the term nullstellensatz. Nullstellensatz doesn't really have anything to do with null, except traditionally, because of that way that you described formally the idea that two things are equal by saying that difference is null. So you could ask, given variable quantities, are there any points where this happens that two things are equal? But that's a null point where they're different. So going through this whole translation, you come up with this idea of a statement that there exists zero, but it really just means points where two things are equal. Anyway, so the null, and then of course the way that's applied in algebraic geometry, you have some equations. First you take the space where the equations are true. And if the system of equations was, quote, consistent, unquote, it means you have at least a non-zero object of your category. But it may not have any points. So the null and such says that it has points. Well, again, points are maps from something that's coming from below. So if below is not algebraically closed, you need this other Galois topos, not abstract sets, in order to talk about it. Because the points, in other words, are going to be defined over the extension fields of the base, possibly. You still say they exist. The original formulation of Hilbert was assuming algebraic closure, of course, in which the points are just maps from one, and you just have abstract sets below. But it's easy to see that that implies, for an arbitrary base field, the existence of points defined over some infinite extension field. And that's exactly what this is, the kind of thing that this is required. So my actual statement, I haven't said it yet, it's just a statement that this canonical map is epic. This map is epic. So intuitively, it's saying points exist. More exactly, it's saying that in every component, in every piece even, not just that the space has points, but every piece of the space has points, where has is the existence in the internal logic of the topos and so on. So every piece has points, existence of points. Now, that's that axiom. It's possible that an analog of my theory would go through without this. This is certainly important for many of the constructions. Shall I say? Well, yeah. Well, okay. Of course, when I talk about equal and different, it's easy to substitute all sorts of stuff under that. I mean to give it a rather concrete meaning, but let's just say that this raises the question, okay, that map is epic. Could it be an isomorphism? Could it be an isomorphism? Could they be equal? Could for a given space, the subspace of points and the quotient space of pieces actually be isomorphic? We have the canonical map. We've said that it's epic, but we're saying could it also be monic, rather than topos? Well, let's think of the example. I told you it was a good example. Reflexive directed graphs. Just think about it. If you have a reflexive directed graph, what would it mean for the map from points to pieces to be a bijective? Well, it would say that every piece has one point. You know what a piece is in the graph. So it's saying that the graph has only loops. Any graph that consists entirely of loops, if and only if. A graph will have this map isomorphic, if and only if it consists entirely of loops. You can have at any number of points. At each point, it can have any number of loops. But that will... Now, in another paper, I don't know if it's... Yeah, that's right. In fact, I should have said, I have published a paper, actually. I mean, sometimes I do that. There's something called TAC, T-A-C, Theory and Application of Categories. a wonderful electronic journal run by Bob Rosenberg. And I actually published something in there last year called Axiomatic Cohesion. So there I give another slightly different example, namely reversible reflexive graphs. Now, reversible reflexive graph means that for every arrow, there's another mate which goes backwards. So there's an operation which to every arrow assigns a reverse, as well as now it turns out that that complicated description is nothing else but just an arbitrary right action of the four-element monoid of all endomaps of the two-element set. Everybody knows what a two-element set is. Everybody knows that it has four endomaps. Two are constant and one is the evolution. So any right action of that is a reversible reflexive graph. Now there is what some people would throw away as a complication they didn't want, but of course that's precisely the sort of thing that encodes all the information in the universe if you want it to. But there are loops which have the reverse. There are also loops which are their own reverse. That's the possibility you might not have thought of first in that description. Every arrow has a loop, and you have loops, of course, but some loops, not all, some, are their own reverse. Actually, if you think in terms of geometric realization by intervals and so forth, it's natural to think of those as sort of, instead of as loops, as they go out and then they come back along the same line. Of course, there are no actual lines, but to picture it, I need to apply the geometric realization. That's the sort of thing that you would get. You go out up to time equal 1/2, and you go back along exactly the same route. T and 1 minus T times 0 to 1, over up 0 to 1/2. Well, so in other words, there are two kinds of loops. So if you do the same thing, you ask which reversible graphs have the property this map is an isomorphism, then you see that it's much more complicated because it's a bunch of dots and then there are loops, but then some of the loops are reversible. So they're reversible, self-reverse. The self-reverse and the others. So the idea is you should think of those as things like atomic numbers. So at each point, one of these apparently stupid objects where this map is an isomorphism, actually at each point you have information of the sort atomic numbers, quantum numbers, or whatever the generic figures are, possible interpretation. So there's a lot of information. So now, you see, what by doing that, what I have done, I take the solution of this equation, which is, at first glance, it's a subcategory V, of course. But that subcategory is really the inverse image, just like this was. This U is a subcategory V. So this is also a subcategory, with both left and right adjoints. S lower shriek and S lower star, calling this thing S. So, obviously, given any graph at all, either reversible or not, but always reflexive, whichever topo you want to be in. Given any one, you can simply take those loops and throw away the interactions. Well, that's the right adjoint. That describes the right adjoint, the S lower star. Instead of taking points, which we're doing at the lower level, we're doing something more informative, more sophisticated. We're throwing away the interactions between different things, but we're not throwing away the self-interactions. So it's just like the points except that this higher up. On the other hand, the S lower street means you take the graph and then you take the components, but you don't just take names for the components. In fact, you keep all the arrows too. Keep all the arrows, except you identify all the dots that are in each component. So in each component, you identify the dots. You get a huge number of loops. Now everything becomes, every previous arrow becomes a loop. So you forced every arrow